Sorry everyone, there's some computer problem. Not a, yeah. So last class we were looking at the Z of 2 sequences, and we also looked at what should be the design philosophy of Pratch. Okay, we looked at what happens when you have multi-path. Because of that, you cannot use all the cyclic shifts that are possible. Okay, so we looked at all these issues. Okay, so in this class, what we look at, we will look at the time and the frequency allocation of Pratch, and also look at the 4 steps of Pratch and try to close Pratch today. Okay, that's what our goal is today. Okay, so the basic idea, I am assuming all of you understand. Essentially, there are Z of 2 sequences, and Z of 2 sequences, when you cyclically, you take a base sequence and you cyclically shift it, what happens is you get orthogonal sequence. You use this, UV randomly chooses this sequence and transmits, and the base station based on this tries to identify the cyclic shift that's done by a UV. Okay, and that's how it identifies the UV. This is a very, very basic idea. Okay, so today what we will do is we'll understand how the UV chooses these different cyclic shifts, what are the constraints that are there. These are the stuff that we are going to look at today. Okay, so any questions before I proceed? Just one small thing. I'm hoping that, I saw that most of you have submitted your homeworks. I request all the other people also to please submit your homework so that we can go. I can give the next homework. Just 1 minute. But now the software crashed, which I used to share my screen. Just give me 1 minute.
Your screen is visible, sir.
Is my screen should be visible. Is it visible?
Yes, sir. Yes, sir.
Yeah. No. What I'm saying
you
is
show basic idea slides, sir.
Yeah. My iPad screen. Yeah. That's right. I just wanted to make sure that. Yeah. This software crash, that was causing some problems. Okay. So let us look at 38211 first. Let's look at 38211 and then take it from there. So 38211, if you go to the 6th chapter uplink, in physical channels, there's something called physical random access channel. Okay, so physical random access channel starts in 6.3.3. Okay, they tell you how to generate the sequences. The sequences is nothing but the Z of 2 sequence. This is exactly what we learned. So there are 2 options in the sequence generation. One is the 139 and one is the length. LRA, remember LRA was the length. I hope all of you can see my screen. LRA is the length. Okay, of this Z of 2 sequence. There are 2 options that are there in 5GNR. One is the 139 sequence and other is the 839 length sequence. Okay, so this 839 length sequence is actually an LTE sequence. Okay, LTE also uses the same Z of 2 sequences. So just to maintain some kind of compatibility and upgrade path, what it was, they also allowed for LRA equal to 839. That has its advantages, I'll tell you. And LRA is 139 was introduced in this 5GNR specifications. Okay, so you find 2 lengths of what the base sequence should be. Fine, that is one big difference in from LTE and NR. In LTE it was only 839. Okay. Then I want to show you a few tables. Okay. Okay, so these are the different Pratch preamble formats that are supported. Okay, so what it means is that, so you can see format 0, 1, 2, 3, and similarly format A1 to C2. Okay, so format 0, 1, 2, 3 are from LT. Format A1 to C2 are exclusive. Are there only in 5GNR. Okay, so both these formats are supported. Okay, so this table tells you what is the subcarrier spacing of random access. Okay, so for example, if you look at table 6.33.12, it is exactly in the same format as 5GNR, 15 into 2 power mu. You can choose mu is equal to 0, 1, 2, 3. So you have 15 kilohertz, 60, 30, 15, 30, 60, and 120 kilohertz. Okay, NU is the length of the sequence, and NCPR is the CP length. Okay, we'll come to this later. For the other Pratch, which is the 0, 1, 2, 3 older formats, you have 1.525 kilohertz subcarrier spacing up to and 5 kilohertz subcarrier spacing. Okay, there are different types of subcarrier spacing. Okay? So the first question that we should answer is, why do we have so many formats? Why can't there be just one format? And second thing is, what is the advantage of having a longer length sequence compared to a shorter length sequence? Okay. Can any one of you provide any pointers on how a longer length sequence helps us? Hello, am I audible?
Last time you mentioned correlation will be good, sir, or longer?
Yes, correlation will be good. See, the longer the sequence, the better the correlation. Okay, so what does it mean? It means that even at the lower power, you will have better peaks in the correlation so that you can identify the user. Okay, so generally what happens is when you go for a larger self, your path loss will be higher, so your SNR will be low. So having longer sequences will help you in doing the path synchronization for large cells. That is one issue. Okay, so even in the same LRA, there are multiple formats. Okay, you see you see this NU is the length of the final length of the path sequences. Okay, so they do some repetition and other things. So one is the base thing. Sometimes it's repeated twice, sometimes it's repeated 4 times, and they're different cyclic prefix lengths. Okay, so all these sequences are made so that you can use the different sequences for different cell configurations. Okay, so some cells, some configuration, some cell for lower cell sizes, some of them are good. For example, the shorter 139 will be good, and for larger cell sizes, the 839 will be good. Okay, depending upon mobility, depending on all the other things, we can choose one of the base station chooses the sequence format. Okay, it's not the UE. The base station chooses the sequence format, and this format is specified to the UE through the SIP1 message.
Good morning, Professor.
Good morning,
This is
sir.
VK. Actually, in large scale, actually the role of SNR is also very important at UE point of
Yes.
interest. So, just to have in that scenario the SNR, poor SNR or better SNR, in poor SNR, in patch, how does the base station determine the poor SNR? Because it is in the patch stage only.
No, sir. So yeah, you are absolutely right. So the base station does not do this on a UE by UE basis. Now it just does it entirely for the cell. The entire cell has only one
entirely
format.
for the cell. Considering the large coverage, considering that it assumes that there might be low SNR and all.
Low SNRs, and you put it. So essentially, when you're doing the cell planning, choosing the format for that particular cell is important.
Right.
Okay.
Sir, excuse me, sir.
Vijay, sir, please.
Hello. Yeah, sir. You said all these documents in respect of UE. You said, sir.
Yes.
But here you are mentioning it's a BTS perspective. Why
No. I'm not saying BTS perspective. See, when I say the documents are written so that it's written from a UE perspective, but this also tells what the UE should expect. The UE expects that one format is chosen. One format is chosen by the base station.
Okay.
It's not UE specific in the sense that, of course, cell has multiple UEs. I will not specify one format for each UE because you don't know at that point, you don't know which UE you are talking to. Okay, so you just do it for the entire cell. Okay, so one more thing that is important is this is called the guard period. Remember the guard period. So this guard period tells us how much timing advance is possible. Okay, so all these sequences have different guard periods. Again, this guard period is related to your cell size and other things. Okay, so you have to make a judicious choice of this patch format. That's what I want to show you. Okay, so if you look at, I'm just focusing on 5GNR. Okay, so there are 13 different preamble formats, each with different lengths, different subcarrier spacing, and different CP lengths. Okay, the preamble format is chosen by the higher layer parameters. How does it come? In the SIP1 message, there's something called the patch root sequence index. One is the patch root sequence index. We'll come to this again, what this means later. This helps us to choose the root sequence. The most important for now is the patch configuration index. So there's a higher layer parameter called patch configuration index, which the base station sends. So this is there in the SIP1 message. If you look at the SIP1 message, in the SIP1 message, if you go through this hierarchy, there's something called ratch config generic. And the ratch config generic, there's something called patch configuration index. It's an integer from 0 to 255. So what this chooses is, this does not choose the direct format here. It chooses one more table. I'll show you the table. Okay, so depending upon you are in FR1 or FR2. In FR1, for example, this is a table called Prash table. So this, it chooses the index in this. So this is it has lots of configurations. Okay, 250, 255. Okay, so it chooses one of these index. So for example, it chooses the index 70. Let's just look at the top thing. Okay, so what does it say? It says, so once you choose the Pratt configuration index, it also specifies the Pratt format in addition to other things. We'll come to these other things later. For example, if you choose something like 90, it specifies that you have to choose A1. Okay, from that A1, you know which exactly format you are talking about. So you understood? So Pratt configuration index gives an index in table 6.3.2.2, which will give you the format that you are choosing. Fine. Okay. So this is good. So this is how the UV will know which format you are choosing. Okay. And the next thing that the UV should know is what is the base sequence and what are the circular shifts that are allowed for that base sequence. Okay. So in that circular shift set, the UV chooses one of the sequence randomly. Okay. So how does the UV determine this? Okay. So it's a little bit complicated, but let's understand this.
Higher layer means at what layer?
Higher layer, when I say higher layer, it means RRC parameters, SIB messages in this case. Okay, so these are specified in the SIB messages. No? SIB messages are there. SIB messages come from higher layers, RRC layer.
RRC, yes.
Yeah. So choosing the random sequences by the UV. Okay, so there will be a set of 64 sequences from which a sequence is randomly selected. Okay, this maximum is 64. But this total number of sequences can also be controlled by a parameter called total number of RA preambles. Okay, this also comes in the SIB message. Okay, but the maximum that's allowed for contention is 64. There's something called non-contention sequences also. Anyway, we'll not go into that in this class. Okay, the total number of RA preambles is 64 maximum. Again, you can choose lower than that based on the base station configuration. Okay, and this will be divided between contention and the contention. Essentially, the total set will be divided by contention base and contention free. So these sequences are cyclic shifts of the multiple base sequences. Okay. So the question is, what are the base sequences? How does the UV know what are the base sequences and what are the cyclic shifts? That is what we should understand. Okay. So we get two parameters from the higher layers. One is called the Pratt root sequence index. Okay. This is not the Pratt root. It's not the U. It's an index for something else which determines U. Okay. And then there's something called zero correlation zone config parameter. Okay, so we learned this last class. Okay, if there is no multipath, technically the UV can choose any cyclic shift. It can choose one UV can choose one, other you can choose two, and other UV can choose three. Okay, but if there is multipath, you have to give gap between these cyclic shifts that you choose. Otherwise, what will happen? They will overlap, and you will not be able to distinguish multipath versus a user. Okay, so based on your cell configuration and mobility, what you should do is you should make sure that there's enough gap between the cyclic shifts that the particular UV that any UV chooses. Okay, so that is determined by the zero correlation zone config. Okay, so zero correlation zone config is a parameter that you set. So for example, depending upon if you set zero, then there is no need for zero is not generally set. If you set, for example, 1, then this corresponding sequences will be separated by 2. If you set 10, then the corresponding sequences will be separated by 19. So depending upon multipath and your cell size, you will choose a particular zone config, zero configuration zone config. And from there, this NCS value is determined. This NCS is the one which in turn tells you how much is the gap between two sequences, the two cyclic shifts that you can choose. Okay. Okay, so Pratt root sequences index is, so what is the Pratt root sequence index? First, let's look at this. So it's a logical index and mapped to the base sequence number in table 6.3.1.3. Okay, let's go to 6.3.3. Okay, do I do this? Okay, I'll do this example in the next slide. Let me do that point. Okay, so as I said, the zero zone, I mean, again, you understand now this why do you require gaps between multipath? Again, it's because multipath, mobility, and other things. Again, this has to be properly chosen, and for every cell planning, you have to choose this. Let's take a particular example and try to create the base sequences and other things. Okay, so I want to choose an 139 length sequence. Okay, what is the example I'm doing? Okay, suppose this Pratt's root sequence index is equal to 4. Suppose they put the Pratt's root sequence index equal to 4. What this means is that means they specify this I. Okay, so I is equal to 4 means, sorry. So we have to choose a table 839 or 139. So let's choose the table 139. Okay, I mean 139. I'll just take the example of 139. Okay, so what do you say? I said I is equal to 4. So I is equal to 4 means 0, 1, 2, 3, 4. So 3 is your base sequence number. So when I say 3 is the base sequence number, what does it mean? It means that in this thing you put u is equal to 3. Okay, remember this u was the one which determines the base sequence number. So you put u is equal to 3. Okay, so if they put I is equal to, for example, 8, what you do? 0, 1, 2, 3, 4, 5, 6, 7, 8. You choose u is equal to 5. Fine. And NCS depends on the zone config. Suppose you put zone config equal to 5, zone config 5 would correspond to 10. Okay, what does this mean? Let's do the example now. So in the document 6.3.3.1, it says your cyclic shift will just focus on something called unrestricted sets. They are type A, type B sets for high mobility. We'll not focus on that. We'll just focus on unrestricted sets. When you have unrestricted sets, okay, your CV is the cyclic shift. Remember how does the UV generate the Pratt sequence? It takes the base sequence and does a cyclic shift with CV. Okay, what are the values of CV that is possible? I hope all of you can see this. Okay, so what is the maximum value of CV that is possible? Different values of TV are possible. It is multiples of NCS. Okay, so from the zone config you can find NCS. And from NCS, you take the multiples of NCS to a certain value, okay, till the length of the sequence divided by NCS minus 1. Okay, so taking this example, okay, so we already know the base sequence in this particular case is first row, fifth column, it corresponds to u is equal to 3. This was what we saw, u is equal to 3. Okay, so for this base sequence, for that one base sequence, if I put a CV now for this particular case, NCS is equal to 10. So every 10th, you can do a cyclic shift of 10, 20, 30, 40, 50, 60. So different CVs that are possible are 10, 0, 10, 20, 30, 40, up to 120. Okay, because 139 is the max. 13 cyclically shift sequences are possible. Okay, so you have to generate this basically based on this particular formula. But only 13 sequences are there. So what happens to the next sequence? Okay, where do I get the next sequence? Then what you do is, so you started with I is equal to 4. The I is equal to 4 corresponds to u is equal to 3 and gives 13 sequence. Then you go to I is equal to 5. If you go to I is equal to 5, then the base sequence number u will be equal to 136. Okay, for that 136 gives another 13 sequence. Next you go to I is equal to 6. I is equal to 6 corresponds to 4. Okay, it gives 13 sequences. I is equal to 7 gives 13 sequences. I equal to 8 gives 12 sequences. When you add all this, you get 64 sequences. So this is how the 64 sequences, different sequences are generated. One thing you should observe is the first base sequence, all the cyclic shifts of 10, 0 up to 120 are orthogonal, whereas with the first base sequence and second base sequences are not orthogonal. Did you understand the generation of these base sequences? I can repeat this if you require.
Yes, sir.
Okay. So there are two parameters you are getting from higher layer parameters. One is the Pratt's root sequence index, and this what is the zero config correlation zone config. These are both there in SIB1. Okay. So from the zero, there's a table. The table number I put somewhere. It's there in the 38.2.11. I'll put the table number. In there, from using the zero configuration zone config, you can find the NCS value. Okay. So this NCS value for unrestricted sets is the minimum gap between cyclic shifts. Okay, suppose NCS is equal to 10, it means that you can do a cyclic shifts of multiples of 10. Fine. So the next question is, how do you find your base sequence? The base sequence is found by this table for 139 length sequence is 6.3.314. The Pratt root sequence index I comes from the higher layers. For example, in this case, it was 3. It was 4. 4 means you go to 0, 1, 2, 3, 4. So this means U is equal to 3. U is equal to 3 corresponds to the first base sequence. Okay. So then what happens with U is equal to 3? You can generate a base sequence, and that base sequence can have multiple cyclic shifts. Yes, you can do multiple cyclic shifts. What are the cyclic shifts allowed? That comes from NCS and basically CV. 0, 10, 20 up to 120. Okay. So these are 13 sequences you will get for that base sequence. Immediately then you go to I is equal to 5. I is equal to 5 will correspond to 136U. This sequence also will have 13 cyclic shift sequences that you can generate from that with the CV. Similarly, I is equal to 6 will give 13. I equal to 7 will give 13. I equal to 8 will give 13, but you choose only 12 because you only require 64 sequences. This is how you generate your 64 sequences.
You said U should be relatively prime with L.
Yeah, U is, 139 is a prime number now.
Yes, in that case, sequentially it can be taken as a 1, 2, 3 instead of alternate columns.
Alternate columns means?
In the previous slide, sir.
Ah.
You, sir.
So saying 3, why did they put 3, 136, 4, 135, 136? Okay, that's actually
yeah, one is increasing order, one is decreasing order. Is
yes.
special reason?
I'm not very sure on why. They might have done some experiments and to find some. See, because correlation across different sequences is. But I mean, let me find that answer and get back to you. Okay, let me understand that. What you ask is a very good question. Why did they make this so complicated? Why cannot they just put 4, 5, 6, 7, 8? Okay, or 3, 4, 5, 6, 7. So why did they do this first base sequence, second base sequence? Let me find out that answer.
Okay, sir.
I think they have done some correlation studies and found that this is the best way. But anyway, you choose from this randomly. Okay. Did you understand? But at least the process from the spec is clear, no? So there are sets called type A and type B sets. So these type A and type B sets are used for high mobility cases, very high mobility cases. In that thing, what happens is, in addition to your cyclic shifts, because of multipath, your Doppler plays a role. And when you have Doppler, what happens is, again, the Doppler in the time domain will result in cyclic shift in the frequency domain. Okay. So for that, they make it. You have to choose it in a different manner. Again, this is given by this formula. But nevertheless, it's always some multiples of NCS. Okay, but what multiple and all those things are a little bit more complicated. We'll not go into that. You just know that there are type A and type B sets for high mobility cases, specifically for high mobility. Okay. So now at this point, what happens? The base station, the UV. So with this higher player parameters, the UV will be able to calculate all these sequences, or at least it knows all the U's and CVs, and from there it will pick one sequence randomly. Okay. So now let's understand how this branch is put in the time frequency grid. Okay, so this is called what is called mapping to the physical resources. So first thing is, branch is a single port transmission. Though theoretically it's not. We should not call it a single antenna transmission, single port. But at this moment, let's think of a port as an antenna, and so we can think of the branch being transmitted on one antenna. Okay. So even SSB, remember SSB was also a single port transmission. Okay. So the generation of branch is specified in how to generate the branch is specified in 38211 in 5.2. It's a little bit different. The equations are a little bit different compared to the standard OFDM generation for the other things. Okay. It's given by this formula. Let's not worry about the formula. I'll explain you what are the parts of it. I just wrote the formula so that you can look at when I'm talking about this other variables here. So any questions before I proceed? Okay. So let me just share my other screen. I will explain you this. This will be a little bit confusing. So let me just explain you with this, and then. Okay. So let's look at the time and frequency of patch. Okay. So remember, everything has to be put in the time frequency grid. Okay. So time frequency, there's a time frequency grid. Okay. This is your time, and this is your frequency. Remember this. Okay. So this, I mean, I think by now all of us are comfortable with this time frequency grid. Okay. So what can happen is patch can occur at different locations of time and frequency. Okay. So essentially these are called patch instance. So the UE can choose any of this patch instance. Okay. So what happens is there can be multiple locations in so on and so forth. Okay. So these particular resources, time frequency resources, are allocated to patch. Okay. So once the UV, I mean, so how does the UV determine which time frequency resources are allocated for the patch? I will tell you that in a minute. But once it knows that the UV has to choose one of these things, the UV will not transmit patch in everything. Okay, the UV can choose one of this and transmits its patch somewhere, and the patch will come in. I mean, suppose the patch came here, then the base station will monitor all these locations, and the base station will identify the patch is here. Okay, is this clear? So essentially, I have to specify in terms of both time and both in terms of frequency. Okay, is this clear? All right. So let us understand how this happens. How many times is repeated in time and how many times is repeated in frequency. Okay, so let's take this example of this thing. Okay, so how many times it is repeated in frequency is given by higher layer parameter called message 1 FDM. Okay, so it can repeat 1, 2, 4, and 8 times or 8 times. Okay, so it can repeat up to a maximum of 8 times. When I say repeat, it does not mean the same. The UE has to transmit and everything. No, that's not what it means. It means that the sequence can happen in one of these places. Okay, these are the possible locations in which the UEs can use to transmit RATch. Okay, so if you look at message 1 FDM, so message 1 FDM is here. Okay, so it is 1, 2, or 4, or 8 are possible. Okay. So how is it specified? So that is one thing. The number of things are specified in that. And so there's something called the initial uplink bandwidth part. Okay, that we'll do in the next after patch we'll do. So the initial uplink bandwidth part is the one in which the initial patch and the PDSCH is used. And that has a specific start point from PRB0. And the patch location is specified in terms of N start array. Okay, this N start array is given by the IE called message 1 frequency start. Okay, so this message 1 frequency start will be providing this height. Okay, and this K bar is provided in the is provided somewhere. Okay, it's provided in the one of the tables. I'll show you the table. Okay, K bar table I'll show you. Okay, K bar is shown there. Okay, so effectively, one thing that all I wanted to take, of course, the details are in the slides. You can read them. Okay. I also do one example. But what you should understand is patch can happen multiple times in terms of frequency. And here I gave an example where the message 1 FDM says it's 2. Okay, just there are 2 options that are available, 1 and 2. Okay.
So just to further understand, sir.
Tell me, Vijay, tell me please.
Sir, for example, there are 4 resource elements allocated by BTS examples. So then 5 users are there. So first few 4 users will be like these RACH resources will be allocated.
No, RACH
again-
resources. No, Vijay. RACH resources are not. So essentially, what the base station tells to the entire cell is, these are the locations in which you can transmit patch. Okay.
This is fixed already.
These are fixed. The UEs
Okay.
will randomly choose. UEs can transmit any one of them.
Yeah. So four UEs have transmitted. So fifth user will wait once 4 UEs complete the setup. Then it will be released, sir, again.
No. It's not like that, Vijay. See, at this point, UEs don't know among anything about themselves, about other UEs also. So this is the first time UE is transmitting in the uplink. Yes.
Yes, sir.
Okay. So let us say there are 4 buckets. So essentially, what the base station is saying is there are 4 buckets that are available. Base station also doesn't know how many users are there who are contending. The users will randomly contend. The first 3 UEs may choose to put in the first bucket itself with different orthogonal sequences. It's all random. We don't know. Therefore, collisions might occur.
Okay.
So it's random at this point. The UE is choosing those locations and UE is choosing the base sequence. Everything is random at this point. Okay. So what?
No, sir, my question, sir, if for example 4 have chosen without any contention, 4 have chosen, sir, 4 are allocated. So now how the 5th user will get the chance, sir? Now when
5th user will choose one of this and will collide.
But already 4 have been occupied, sir. So when it will be released, sir, again for the...
No. The question is, how does the user? I mean, see, okay. I understand your question. So Pratt's process is a continuous process. Okay. So
Yes,
I mean, so it knows the resources. So base station is transmitting. It tells the users in terms of SIP1 messages that these are the resources allocated for Pratt. Okay.
Yes.
And these resources occur periodically. Every 20 milliseconds or so it occurs. Okay. So in any of this 20 millisecond thing, users can contend. Okay. Once user contends and once it locks off, it doesn't contend again. Huh?
Yes, sir.
Yeah, again, it will go into, then the base station will allocate resources some other place and they will be happy. Only the new users who come and who were not able to successfully contend in the previous case, again contend.
Okay, got it.
Okay. Where are we? So if you look at this, so there's a table that says, so for each of this, again, you can see the table number. So for each of the supported, for each of the supported lengths, what is the delta FRA for Pratt and delta F for PUSCH? Based on that, it tells what is the number of resource blocks, okay? Number of resource blocks that are required. Okay, so for example, let's consider the case that delta FRA equal 30 and delta F 30. Okay, so 30, 30, 139. Let's take this case, where my cursor is. So 12 RBs are allocated. Okay, 12 RBs are allocated. So 12 RBs means 144 RE are allocated. So 144 RE will fit the 139 length sequence. But where does this 139 sequence start? The 139 sequence from the base point, it says that the starting point is 2. So 2 REs will be left and the 139 sequence will be put here and 3 RBs will be left on the other side. Did you understand this? So what happens? This is the start of the initial bandwidth part. From the initial bandwidth part, NRA start into NRBSC is given by this called message 1 frequency start. That is that message 1 frequency start is nothing but this height. And this K bar is given by this table for each LRA and delta FRA where you can, this is K bar. Okay. And from K bar, you can put the patch in the frequency domain. Okay, whatever length sequence, and some of them, some of the end, the things will be left empty. Some few REs will be left empty. Okay. So the number of the resources that are allocated to patch are made sure that it fits in. For example, if you consider the case of delta FRA is equal to 1.5, 1.25, and delta F equal to 50 in the first case. Okay, 6 RE are allocated. This 6 RB are allocated. This RB is in terms of a PUSCH RB. Okay, so 6 into 12 into PUSCH RB is 15 kilohertz in this particular case. And if you're putting 1.25 kilohertz patch thing in this 115 by 1.25, so you totally get 864 REs in terms of 1.25 kilohertz spacing. So 839 line sequence fits into that properly. Okay, so they made sure of this table. So you understood allocation. So I mean, I would just suggest you to read the slides once more, and wherein I look at the formula in great detail and I explain what this is. But what I want to tell, what are the highlights that you have to take from this slide is, the higher layer parameters specify the location of patch in terms of frequency. One is called the FDM start, message one frequency start, and the other is the K bar. K bar comes from a table, and the number of patch repetitions is given by the message one FDM. Okay, so essentially patch can be repeated multiple times in the frequency domain. Fine. Now let's look at the time allocation.
So this 839, 864 we got in the last. That also could be means even 139 format, 139 sequence format could be used there.
No, sir. So essentially, I mean, that will be waste of parameters now. So waste of resources. So for 139, I mean, so the sequence length is also specified here. So for 139 only you can use this set.
No, okay. Suppose I got somewhere between 400. How can I fit it either in 139 or?
No, you will not get like that. These tables were made sure that it's very close to 139 or 839.
Okay, okay.
They are made sure. I mean, you lose like 3-4 REs, nothing more than that.
But that RE is left is also intentional, or it is because of just fitting it?
There are two reasons. One is that in the frequency domain, you can do some filtering and for the base station to base, so that the other resource elements don't interfere with in the patch detection. That's one thing. And second thing is you cannot start another user for some other thing. You cannot start in the between an RB. So this has to be left.
Okay.
These are waste. These 3 REs. In this particular case, 5 REs are getting wasted. Okay. So now let's look at the time allocation. So if you look at the time allocation, again, so what happens is, remember we have the patch configuration index. Let's take the example. So that with that you choose a row in the table. Okay, whether it's FR1 or FR2, I'm choosing the FR1 table. So suppose you choose 71. Okay, 71 means A1 format. Then the next thing tells you which system frame number. You remember system frames. System frames go from 1 to 1023. Sorry, 0 to 1023 or 1024 frames. Okay, which of the system frames have patch? So for example, in 70, let me just increase it a bit. 70, it says x is equal to 2, y is equal to 1. So NSFN mod 2 is equal to 1 means NSFN, so all odd frames. So all odd frames will have, what do you say? All odd system frames will have the patch. That's what it means. Okay? Understood that? You put the x and y, it says NSFN mod in the 70 case, NSFN mod 2 is equal to 1. NSFN, something mod 2 is equal to 1 means that the number, as that something should be odd number. Okay? So it says that odd, for example, in the patch case of 70, odd frames have patch. Okay? So odd frames have patch means each frame is 10 milliseconds, remember. Okay, so the gap between, so every 20 milliseconds it repeats. Okay. So the next thing is, which in that system frame, which subframe? There are 10 subframes in a system frame, remember. So which subframe it starts? For example, in 70, it says the subframe number is 9. Okay, the subframe number 9. In the subframe number 9, it tells what is the starting OFDM symbols. It tells you that. Sorry, I'm just aligning this. What is the starting OFDM symbol? And then in that, it tells you, I mean, I'll come to this other two parameters later, okay? So at least this table tells you exact time locations in which your patch is there. Okay, so how does the time allocation happen? Okay, how many times does it repeat in time? It's a little bit weird. Okay, so that you can determine by looking at these earlier tables of formats. So every time the format, it's written as 4 into something, 6 into something, 8 into something, or so on. Okay, this pre-multiplier tells you the number of times the patch sequence is repeating. Okay, so in this particular case, for example, if you take the A2, it says you can repeat it 4 times. Okay, and then there's a CP. So the way path sequences are put is, the sequences are repeated and the cyclic prefix is put once for all in the before. It's not put for each sequence. The cyclic prefix is put for all the sequences, repeated sequences, once they put the cyclic prefix. Okay, the number of times the cyclic prefix repeats is given by this. By looking at this front parameter, you can tell how many times the cyclic prefix repeats. Okay, so sometimes it repeats 2, sometimes it repeats 4, 6, and other things. Is that fine? So let's take a simple example. Okay, let's take a simple example, and I'll come back to the other slides. Okay, so in this case, I'm taking the example of 70, branch configuration index 70. Okay. Okay. If you take 70, it is A1. Maybe I'll make it full screen so that you can see it a little bit better at least. 70 is A1. A1 means we saw that it's there in all odd subframes, all system frames. In that, this subframe number is 9. The starting symbol is 0, and the number of Pratt slots within a frame, within a subframe is 1. Okay, so if 70, if you look at number of Pratt slots within a subframe is 1, means only in one slot will the Pratt be. Okay, and the number of time location, the next thing is number of time domain Pratt occasions in a Pratt slot is, in this case, is 6. So the Pratt is repeated 6 times in that slot. Okay, so for in this particular example, if you take the SFN, it's only in the odd SFN it is there. In that odd FSF, sorry. In that odd SFN, only 9th subframe has it. In the 9th subframe, just 1 minute.
So here, number of time domain patch is equal to 6 is set. Means 6 symbols will be allocated.
Sorry?
So here, number of time domain patch occasions within a patch slot is equal to 6.
6 means the sequence will be repeated. The already A1 has repeated twice. Okay, so this particular thing, where let me just open up my pen. Not pen, sorry, just 1 minute. Okay, so this will repeat 6, and so this 2 corresponds to 1, 2, 3, 4, 5, 6. Okay, the number of, so this is called a Pratt, one Pratt occasion. Okay, the Pratt occasion happens 6 times. Okay, that is what this number 6 is, number of Pratt occasions within a slot. Okay, and the Pratt duration is 2. The Pratt duration was 2, no? This is the 2, 1 and 2. It repeats 2 times. That's what it means. Pratt duration is 2. Okay, I'm just trying to understand why does it start in 14th. Lowest.
So it is starting in the second slot, I think.
Wait.
30 kilohertz.
Yeah. So when now see, essentially this thing. This one, right? Yeah. You have to look at this. If the number of Pratt slots within a subframe is equal to 1, then NA slot RA is equal to 1. If it is not 1, then it's equal to 0, 1. Okay, so there's a formula for that. So when when it becomes 1, it is there in the second slot. Okay, I mean you have to put it in the formula of L. L is the starting OFDM symbol number, so it starts from 14th slot, and when our NRA slot is equal to 1, it becomes from 14th. That's why it comes. Okay, so from 14th symbol OFDM symbol it starts, which is the second slot. You have 1 Pratt occasion, 2nd Pratt occasion, 3rd Pratt occasion, 4th, 5th, and 6th Pratt occasion. That's
So is this not colliding with that SS block, sir? SS block we have.
No. So this is there in a different frequency location. This will be there in a different frequency location. Remember, there's a frequency and time. I'm just showing the time part of the thing. Remember the grid always.
Okay, sir.
So if you look at the grid, okay, the SSB may be somewhere here. It's okay, it doesn't collide. Or it may be here also. I mean, I'm just showing examples. This may not be even correct. Okay. So what I'm now showing is this time locations. Earlier I was showing the frequency location. So in time frequency degree, they'll be separated somehow. Okay.
Okay.
Okay. So now if you take a different example, suppose your patch configuration index was 74. Okay. If you look at 74, it says the number of patch slots within a frame is 2. When you say 2, automatically it becomes 0, 1. The number of slot locations in RA will become 0, 1. Okay. So it starts in the first slot, and it's there in both 8 and 9. Subframe number is there in both 8 and 9 here. Look at this. Okay. Sorry, wait, is there 8 and 9? Yeah, 74 corresponds to 8 and 9. So it's there in both subframe number 8 and subframe number 9. In the subframe number 9, it starts in the, what slot does it start? It starts in the first slot. It starts in the first slot, and that particular OFDM symbol number. Okay, so you can see that it's there 2 times. Okay, so these many times. So the UE can choose any one of those. It does not mean that UE has to put this patch in all these things. Okay, so there's enough flexibility so that UEs can choose this randomly and avoid collisions. Is that fine? I don't expect you to understand, I mean, to memorize all these things. I'll give you some particular homework problems where I'll ask you what is the patch locations and other things. You can then read this and try to determine which places you can put your patch. Okay, that's how it becomes clear. I mean, there's nothing more to explain to this. Okay, so one thing I want to highlight is, so for each of these things, for example, for the NR things, I calculated the patch length. The patch length is given by this. The patch length is nothing but NU plus NCP length. Okay, and the total OFDM length that I have. The total number of OFDM symbol length that I have from I found out this from this table. Okay, sorry, not that table. I mean, where did I find this from? Okay, the closest OFDM tail length, OFDM symbol length. Okay, the closest OFDM symbol length, and then I did guard period is nothing but this minus this. Okay, guard period is nothing but this minus this. So this is the guard period that's available for timing advance. So if you choose A1, A2, A3, you will not have too much guard period. So essentially, effectively, this means there's like an indoor preambles. Whereas the other B1, B2, B3, B4 are outdoor preambles in some sense. Because there's a guard period, you require this guard period so that you can do timing advance. Fine. Now let's go to the patch procedure. Any questions before we proceed? So let's start the patch procedure, the 4-step procedure, and let's try to understand this. Okay, the step 1. The step 1 is done by the UE. What does the UE do? The UE looks at the SIP parameters, MIP parameters, determines where all the locations at which he can transmit patch. What is the format of patch that he has to transmit? What is the allowable cyclic shifts that the patch is allowed, I mean, the UE is allowed for? All that we have discussed before. And then it randomly picks out a sequence. Okay. And then what does it do? It transmits. It transmits in one of the patch occasions. Okay. Then the base station. So at this point, what happens? The random access preamble transmission is done by the UE. The base station, what does it do? It will, what do you say? It will monitor all those locations and understand that some UE transmitted in this particular time frequency location. Okay. And this was the timing advance of that particular UE. And it will also understand what is the base sequence that was transmitted. So what are the things that base station will do? It will understand what is the base sequence that the UE transmitted, what is the timing, what is the circular shift that the UE has used, the timing advance, and at which time frequency location. We have seen that multiple time frequency locations are possible. Now, you will also understand which time frequency location that the UE has transmitted. Okay, so this is called the step 1 of the random access preamble transmission. Okay, is this clear? The step 1 is clear? Any questions? Okay. Step 2 is done by the base station. Excuse me. Okay. So in step 1, what did it find out? It found out that what did it find out? It found out the base sequence. What is the base sequence used? Was the cyclic shift it used. So next thing what it does is it does something called random access response. So in the random access response, it puts the preamble at index. When I say preamble index means what is the base sequence and what is the cyclic shift. It's called the preamble index. Okay, it puts the preamble index inside whatever it's transmitting, broadcasting. Okay, along with the timing advance and a temporary TCRNTI, temporary RNTI, radio network terminal identifier. A terminal identifier is allocated to it, along with a uplink grant. Uplink grant means this is the grant. It is allocating some resources to that particular UE. So what at this point the base station does not know the UE name. It only knows what the UE has sent in terms of the preamble index. Okay. So what does it do? It puts in a packet the preamble index that it has identified. Okay. Along with the timing advance that the UE has to do, along with some resources for uplink. Okay, in terms of what is the frequency resource allocation, the time resource allocation in the uplink. Okay, and then it also puts something called a temporary identifier for the UE. It says you are identified by this temporary number for now. This is called TCRNTI, temporary cell RNTI, TCRNTI. Okay, okay. So now what happened? Let's get back. So in the first step, UEs have transmitted. Okay. In the second step, the base station has heard all these UEs, and for each UE, it makes a packet like this. Okay, for each UE, it makes a packet like this for whatever it has identified, and then transmits it back. Okay.
What is frequency hopping flag here?
Where?
In table 8.2.
Yeah. So in the uplink, you can do frequency hopping. Okay, I mean, when we do the uplink PDS, PU, CH transmission, I'll tell you. So you can do frequency hopping in the sense that what happens is you instead of putting contiguous things, you do some kind of scrambling in the frequency domain. Okay, we'll come to that when we do that. For now, let's just forget about this. Okay, if it's there or not, there, it doesn't matter for our case at this moment. Mainly to get frequency diversity in the uplink. Okay. So now what happened? So each UE knows what preamble it has transmitted, what CV it has transmitted. Let's for argument assume that for some based on luck, all the UEs have chosen different preambles and different cyclic shifts. Okay. So now when the base station sends the message back, each UE can identify, because the UE base station is also putting what is the preamble index that it has found. Based on that, what will happen? Each UE will be able to identify, oh, okay, this is for me, this is for me, this is for me in the downlink. Okay, so it will be each of them will be able to decode their own MAC PDU, and from that MAC PDU, they will be able to identify the temporary RNTI. Okay. Then this is the third step. In the third step, what will it do? It has a temporary CRNTI. Each UE will, sorry.
So in step 2, I have a question. In
Yes.
step 2, what frequency and time resource G node B is using to send this?
Yes, perfect question. So this is there in SIB1. There is something called as initial bandwidth part. We saw the initial bandwidth part. Nah? In that initial bandwidth part, there will be some resources which are meant for this random access response, RAR response. So the UVs will go on monitoring that particular space. Okay.
Okay.
That is called RAR window also.
So this is, so by the way, in shortcut, people call this RAR, random access response. So RAR window is something, sir. RAR window means, so in the first step, you transmitted, the U is transmitted.
Okay.
So then what might happen? I mean, if the base station successfully decodes, was able to identify that, and then the base UE waits for the random access response. The maximum time for which the UE waits is called the RAR window. After that, its timer expires, and then it again goes back to step 1.
Okay.
That's called the RAR window. Okay, again, even that RAR window is also specified by the SIB1 message. It's there. I mean, if you check that, we'll understand that. Okay. So now what will happen? The terminal, in this third step, now the base station has identified some resources for the uplink. Okay. So each terminal, what will it do? It will put their own identifier called the CRNTI. I mean, I think it has something to do with SIM and other things. Okay. The core network terminal identifier, it's called as. I mean, not core network, so that's not the correct. CRNTI will be sent. This is a UE identifier, along with scrambling done by the temporary TCRNTI. Okay, TCRNTI is what has been sent by the base station. The scrambling happens there. Okay. So at this point, the base station in the step 3 is what the base station receives. Okay, at the step 3, it will immediately know, okay, this is the permanent identifier of that particular UV. Okay, because it already has sent the TC identifier, it can now receive, once it receives this packet, it knows the TC identifier, it knows the other identifier also, the UV identifier. So it knows that. Okay. Step 4 is called the contention resolution. Okay, this is mainly to identify if users have collided. Okay, so why this happens? So in step 1, what happens? We see if step 1, if all the UVs have transmitted different orthogonal sequences or different base sequences, we are fine. But by bad luck, what might happen is 2 users might have chosen the same time frequency grid and same preamble index. The preamble index means circular shift and base sequence. Then what will happen? In the second step, suppose the base station was able to decode that. Okay, it's just a peak now, so the base station will be able to find the peak, and then it will identify that, okay, this is the preamble index, this is sent. The second step, this is the packet that the base station sends. Then what will happen? Both the UVs will look at this rapid, which is the preamble index, and say, oh, this is for me. Okay, and in step 2, both of them will feel, both the UVs will feel that, okay, this is for me. Okay, and what will they do in step 3? In step 3, both of them will transmit in the same frequency time resources in the uplink. Okay, there are 2 things might happen in step 3. So both of them will collide, and the base station will not be able to identify anything. Okay, so once the base station is not able to identify both these packets, then step 4, what will happen? Step 4 packet will not come from the base station to the UV, both these UVs. Okay, and the UVs will time out and then restart the process. Maybe what might happen when both of them collide, one of the users might get decoded. Okay, when that happens, sorry, if that happens, step 4, what will happen? Because the correct identifier of the UV is sent in the step 3, the base station in the step 4 will send back that identifier back saying, hello, this is for this particular UV that I am sending the resources. Okay, that is why step 4 is called the contention resolution. Okay, mainly in the case of a collision, it helps the base station confirm the UV identity to the UVs. Okay, I just put a summary of this thing here. You just have a look at it and then we'll discuss the issue. We'll discuss. I'm pretty sure that there are some questions. Any questions? Did you understand all the step 1, step 2, step 3, step 4?
So will it differ in case of FDD and TDD kind of environment?
No, sir. It's only question of where the resource there, where the path slots are there will differ, but this process I don't think will differ. Okay. So
Please repeat. In case of the collision, the UE will wait for some time, or what will be there?
So step 1 you understood, step 2 you understood. Step 3, what happens? Both of them will transmit the same frequency time resources, sir. Okay? Collision will happen. So there may be two possibilities. Both of them can never be decoded. Okay, because if SNR of one thing is high, it's SINR, the signal interference noise. If SINR of one user is large, the SINR of the other user will automatically be low. So only one of them will be decoded, at most, or 0 will be decoded. Okay, if 0 are decoded, if none of them are decoded, then there is no step 4 message will not come for both the UAs.
Yes, that I was thinking.
Yeah, and after some time they will time out. If one of them gets decoded, one user will not get a message, the other user will get a message, and the user who will not get message will time out.
Right.
Okay.
If you can also explain the purpose of long sequence and short sequence.
Yes, sir. Yes, sir. So long sequences are mainly for large cells, sir. Okay, they're very mainly for large cells. Because what happens is when you take longer sequences and correlate, the energy in the sequence is large. First of all, if the sequence is larger, the energy is larger.
So, but UV may not know whether it's in large cell or small cell.
UV will not know. The base station knows. No? So the base station is the one who is telling the UV to pick up A1, A2, A3, or whatever 0, 1, 2, 3 formats.
Okay, so G node B is already informing as part of SIB messages?
SIB1 messages.
Okay.
So for example, I'll show you that where that happens is, it says something called Praj config index. Okay, this Praj configuration index is nothing but
So what are the key parameter in MIB and SIB which UV is using during the press process? One is this long.
So it's this one, sir. So in SIB1 message, there's something called serving cell config. In serving cell config, this uplink config SIB, common SIB. The uplink and this bandwidth uplink common. In the bandwidth uplink common, there's something called RAJ configuration common. This RAJ configuration common has all the parameters that are required. Okay. So for example, total number of preambles, and there is this thing Praj configuration index. Message 1 FDM is the number of times it's repeated in the frequency domain. Message 1 frequency start is the frequency location of the Praj. Okay, 0 correlation zone config using the NCS table. Okay, so all these parameters are highlighted in the in the slides. Okay. So I'll just take 5 more minutes, and I will stop by introducing this particular thing. So this is the first time that the UE is transmitting in the uplink. Okay, what should be its transmit power? Okay, so generally once everything is established, then the UE does power control so that some kind of SNR is maintained at the base station. Okay, but this is the first time it is doing its Praj. In step 1, for example, what is its transmit power that it should use? Okay, so what the UE does is, in a nutshell, the UE first tries to estimate the path loss based on the SSB power, the SSB receive power. Okay, so there's an SSB receive power, and also there's an SSB transmit block power that's transmitted. Based on these two, this again, the SSB PBCH block power comes in the SIB1 message. Okay, based on the received power it receives from the SSB and the approximate transmit power that is there, it will be able to find out the path loss. Okay, so from the path loss, what will it do is, there's also something called preamble received target power that the base station specifies. The base station specifies that this is the target power that I require so that I can decode. So either you should be better or it should be better than this number. Okay, so based on that, it will increase its power subject to a maximum power constraint of class 1 or class 2 or class 3. It will increase its power. Okay, so what happens is, first time it does the transmission, Praj 1 transmission, it does with this particular formula. Next time, what does it do? Next time it transmits Praj, it improves its power, increases its power by something called a power ramping step. It's also provided there. There's a formula for this. Every time you do this, there's a particular formula in which you have to increase your power. Yeah, of course, it's all subjected to 23 dBm for a normal handset and 26 dBm for a class 2 handset and so on and so forth. Okay, so it goes on increasing its power till it hits. If it doesn't lock on, then it means there's some other problem. That's how it does power control, initial patch power control. Okay, is this clear?
Yes, yes.
So one thing you should understand is that the base station should do a lot of configuration when you set up the cell. It's not a, I mean, a lot of parameters have to be set properly so that everything works well. Okay. So I'm going to stop now. In the next class, I'm going to talk about the initial bandwidth part, and also this something called Patch SSB association. It just takes 5 minutes. I'll do that in the next class. And then we'll move to a newer topic in the next class. Okay. So thanks everyone. I request everyone to submit your homeworks. I will put the next homework on Patch. Again, a theoretical homework on Patch, where I will ask you to find out the preamble numbers and other things so that you will have a good understanding of the system. Okay. Thanks everyone. See you on Tuesday.
Thank you.